Another equation that comes up a lot is the heat equation. Now, most often the heat equation is used to model temperature and temperature differences within an object, but it can also be used for concentrations or spread of diseases or various other similar quantities there. So let's see the heat equation. Here is the heat equation in a single spatial variable. We have that the change of temperature with respect to time is equal to a constant dependent on the material, or perhaps dependent on the units involved, multiplied by the second derivative of the temperature with respect to position. What this means is if at a particular point a particle is hotter than its surroundings, the second derivative will be negative, and this particle will cool by giving heat to its neighbours, whereas if the particle is cooler than its neighbours, the second derivative will be positive, and the particle will gain heat from its neighbours, and the temperature will increase. It is also worth pointing out that as the only places that the temperature T appears here is within derivatives, it applies just as much to, for example, the centigrade or Celsius scale rather than the Kelvin scale, or also it applies to the differences between a given temperature and the ambient surrounding temperature. So in examples involving the heat equation, if we talk about T being 0, that does not necessarily mean absolute zero. It could just as easily mean the same temperature as the surroundings. The heat equation can also be extended to more dimensions. Here we see it with 3 spatial dimensions. Here we simply add the second derivatives. So let's see an example. We're asked to show that the temperature profile here, e to the minus t times sine x, satisfies the heat equation with the constant equal to 1 here, along with the conditions that are mentioned here. The temperature is 0 when x is 0 or pi, and the initial temperature when t is equal to 0, t is equal to sine x. We're asked to show that this function here satisfies everything mentioned below. We're asked to show that the temperature profile here, e to the minus t sine x, satisfies the equation and it satisfies the condition. Well, to start with the equation, we need the derivatives here. So here's our t for temperature, e to the minus t times sine x. So we need the derivative with respect to time. dt by dt, we differentiate the exponential minus e to the minus t times sine x, and now we'll find the derivatives with respect to position x. So dt by dx, that will be e to the minus t times cos x, and then we differentiate again, d squared t by dx squared. Cos will differentiate to minus sine, so we get minus e to the minus t sine x. We compare the two here, and we note that dt by dt is equal to d squared t by dx squared. The equation is satisfied. Now we have the conditions, so let's see what happens. Firstly, at x equals 0, our t here will be e to the minus t times the sine of 0. Sine of 0, of course, is equal to 0. Similarly, when x is equal to pi, our temperature T here will be e to the minus t times sine pi, and sine pi is also equal to 0. So once more, t is equal to 0. And then, putting in our value for t, when t is equal to 0, we will have that our temperature T will be e to the minus 0 times sine x, and of course e to the 0 is 1. So we simply have that t is equal to sine x, so we say that the conditions are also satisfied. So our temperature profile here, it does indeed satisfy the equation. It does indeed satisfy the conditions. So let's see what happens when we try to model the heat equation. Here we have an initial heat profile, T is equal to sine x, and let's see what happens as we allow it to evolve. You can see the heat decreases, the temperature decreases down towards 0. We watch it again, decreasing down towards 0. Now when it starts, we see that we have the temperature profile here where the second derivative with respect to position is negative. So that means that dt by dt will be negative, and then our situation will cool. So let's let it cool for a little bit, and then just stop it after a while. Now we see that the second derivative is still negative, but it's less negative than it was originally. It's not quite so strongly curved, so the rate of decrease of temperature has decreased. It's slowing down, and it gets slower and slower as the temperature smooths out. So for example, around here, where we've stopped it once more, the second derivative, while negative, is not too far from 0, so it's almost stopped in terms of the decrease. It decays as an exponential down towards 0. But let's look at different situations here. Here we see a situation where we'll start with a heat profile as shown here. You can see in places such as here and here, the second derivative with respect to position is negative, whereas here the second derivative with respect to position is positive. We would expect the temperature to decrease here and here, but to increase here. So we'd have heat flowing here and heat flowing here. So let's evolve it and we'll see what happens. Let's look again a bit more slowly. We can see that in the middle the temperature does increase. Either side the temperature does decrease. And fairly soon we are in a situation where the second derivative is negative everywhere, and the temperature does now slowly decrease. now that we've reached a situation like this, it does resemble the original sine wave that things started from. Let's also imagine a situation where we start from a triangular wave such as this. You can see that along most of the profile, the second derivative is equal to 0. It looks like straight lines, whereas near the peak, very localized to the peak, the second derivative will be negative. So we would expect heat to decay quite rapidly near the peak. So let's set it going and observe. Indeed, we see the temperature decreases at the peak. It causes curvature everywhere, and then once more, fairly soon this settles down to something that resembles the sine wave and decays exponentially, as did the other cases. Again, decays in the center first. This causes curvature. The second derivative is negative everywhere, but more smooth now, and it decays slowly.